So yeah, good afternoon, yes, and welcome again to the Communication and Signal Processing Seminar. So yes, we are running everything online, and so I would want to first start with just thanking a few people. I guess our sponsors, which is KLA, and the research areas, which is the Network Communication Information Systems and the Signal Processing, Signal Image Processing Machine Learning Group. Furthermore, I should also thank Shelly, who's behind the scenes doing a great job putting everything together and contacting the speakers and making sure everything is running, including the gather town where you're meeting speakers. So as I mentioned, like last time around, there are new things in this component. We do have this gather town meetings with the speakers. So I think that some of you they've already met with her. And we also have discussants. So at the end after Nicole finishes, two of us here today, me and Sheetan, are going to talk. And this is to either provide different perspectives or discuss some points in depth. And part of it is to increase engagement. So anyway, let me start by introducing Nicole and then let her take the floor. So Nicole Immorlica is a researcher at Microsoft, New York. Her research lies broadly in the field of algorithmic game theory, using tools and models and concepts from both theoretical computer science and economics. She hopes to explain, predict, and shape behavioral patterns in various online and offline systems, markets, and games. So her area of specialty includes social networks and mechanism design. In fact, a few years ago, she was the program committee chair for EC, which is a premier conference which brings in algorithmic game theory topics together. So she received a PhD from MIT in 2005. Then she completed 3 years of postdocs, both at Microsoft Research in Redmond, the other side of the country, and then CWI in Amsterdam, before joining as an assistant professor at Northwestern in 2008. And I've known Nicole as a colleague from my days at Northwestern. We had significant overlap. And then she joined Microsoft Research New England in 2012, where she continues to be New York office and the New England office are there together. So I'll give Nicole the floor. Please go ahead, Nicole.
Hey, thank you. So I guess maybe I first met you actually in Ireland, as I recall. Is that right? Or...
Actually, at ITA, mate. It was one of the.
Right, at ITA, yeah. So a long time ago. The trip to Ireland was beautiful.
No, Ireland
always meant to go back. But anyway, so I'm going to talk today about incentivizing exploration with selective data disclosure. This is joint work with Jiming Mao, who was an intern at Microsoft at the time, is now a researcher at Google Research, Alex Lifkins, who's my colleague at Microsoft Research, and Stephen Wu, who was a professor at the University of Minnesota and is potentially in transit between there and CMU. I don't know where he is physically given the state of the world, but is joining the CMU this year. So as I said, I would like to talk to you guys about incentivizing exploration with data disclosure. And let me first talk a little bit about what I mean by incentivized exploration. So I have in mind a model in which agents sequentially choose actions, and then they're going to receive a stochastic reward that's drawn from some unknown distribution. There are many applications you could imagine for this setup. For example, you might want to imagine that the agents are customers entering some online store, and they have to pick which product to buy. Maybe it's a laptop or a car, something they buy fairly infrequently. And their utility for the choice of product they make is the quality of the product itself. Here, notice that I'm assuming that there's a common value. All agents have the same value for any particular laptop, which is the quality of that laptop. Another application that's talked about a lot in the economics literature is choosing medical treatments. So here you come down with some rare form of cancer and you have to pick what treatment to undergo. And there might be a different set of medical trials you could try, and your utility for a selection is the health outcome. But you don't know up front the health outcome of each various trial. The health outcomes are some stochastic outcome drawn from an unknown distribution. And so this is, a very natural sort of exploration setting. The twist in the problem that I'd like to study is that these choices aren't just arbitrary choices of the agents, but rather the choices are coordinated by a principle. In sort of running example you can have in the back of your head throughout this talk is recommendation systems. So think about Yelp, for example. I searched for pizza in Yelp when preparing these slides near Greenwich Village, which is around where I live in New York City. And it presented me with a bunch of options for various pizza restaurants I could go to. One is Arturo's. It had 4 stars and 678 reviews. Another option was Prince Street Pizza, which had many more reviews, 3,463, and more stars, 4.5 stars. And so, Yelp presents me with some sort of information, and then I make a choice, and my goal is to go to the pizza restaurant of the highest quality. So in this kind of setting, there's some trade-offs. The principal, Yelp, for example, would certainly like to maximize the welfare of their customers. And in order to do so, the principal needs to both explore potential new, pizza restaurants. There's many pizza restaurants in Manhattan, and Yelp needs to explore different pizza restaurants in order to learn more about them. But Yelp also would like to exploit, that is, provide each agent with enough information to make the best choice possible. And that's, in the principal's incentive to do so, because exploitation will improve the welfare for that particular agent. But the sort of misalignment of incentives between the principal and the agent arises from the need for exploration. And this is because the benefits of exploration are only accrued by future agents and not the current agent. And so this raises a question of how can a principal encourage agents to both explore enough and also exploit enough in order to maximize the long run welfare. And prior work has thought about this question and ways to leverage either information asymmetry between the principal and the agents, or payments from the principal to the agents in order to induce an optimal amount of exploration. Our results, we're also going to leverage this information asymmetry to induce optimal amount of exploration, but we're going to do so in a restricted model. We're going to restrict the principal, so a platform like Yelp, to use a subset of messages, which we call selective data disclosure. The messages that the principal can use in our model is a subset of the history of reviews on the platform when the current agent arrives. So the platform can choose which reviews to display to the current agent in an attempt to convince the agent to potentially explore. But the key point here is that the platform has to do so in an unbiased way. So I will not allow the platform to pick the reviews to display to a current user based on what they say, but only when they were written. And I'll get into the form of that policy a little bit later. Hand in hand with that, I'm going to assume a behavioral model of the agents. I call these frequentist agents, and they're going to act based, so they're going to, form some assumptions, some beliefs about which restaurants have the best quality pizza, and they're going to form these beliefs based on the empirical mean of the reviews that they're shown by the platform and the number of data points in this that were used to compute this empirical mean. And notice this is precisely the information that Yelp provides with me, for me. It provides me with an average star rating and a number of reviews that resulted in that star rating. So what we're going to see, this is our model, and the results that we're going to see is, first we're going to look at a simple policy that divides agents into focus groups and collates their data in order to get low regret with respect to the optimal reward. And then that's going to be a suboptimal regret bound. So we're going to slowly work our way towards an optimal regret bound by increasing the interactions between agents, the information flows between agents. So let me start with a very brief background. I think that this audience is probably pretty familiar with the multi-arm bandit work, but since this, this is sort of an extension of that model, I think I need to make sure we're all on the same page there and explain the difference. So in the multi-arm bandit literature, we have a centralized planner that's sequentially choosing actions and receiving a stochastic reward from an unknown distribution. So the difference is that the planner can trade off exploration and exploitation, and it's in her interest to do so. And she doesn't need to convince an agent to try and explore. In other words, there's no incentive constraints in the multi-arm bandit problem. There's many applications of this in computer science and other fields, and so it has a long literature behind it. And what we'll see is some of the algorithms we develop mimic the traditional algorithms in the multi-arm bandit literature, but in a way that enables them to succeed in the presence of incentive constraints. And in case you are not yet familiar with the multi-arm bandit literature, I just wanted to give a shout out to the textbook of my co-author Alex Slifkin's Introduction to Multi-Arm Bandits, which was published in Foundations and Trends earlier this year. I think it's a very nice introductory level, very clearly written introduction to this area. So if you're looking for something basic to learn about the multi-arm bandits and the incentivized exploration as well, I encourage you to take a look at that book. So to be a little more precise about the terminology, I'm going to borrow the terminology from multi-arm bandits, in which you're given actions or arms. I'll probably use these terms interchangeably. Time horizon, capital T, and the planner in each step chooses at most one arm. The arm is then going to yield a reward from an unknown distribution. I'm going to assume what's called in the literature bandit feedback. That is, the planner sees only the reward of the chosen arm, but not what reward she would have received if she had chosen a different arm. And I also will assume that the rewards are IID, that is, that they're drawn independently from a distribution that depends on the arm, but not on the time at which the arm was chosen. And one thing to note here is that I'm working in a model called stochastic bandits. This is actually somewhat counter to the much of the literature in economics in incentivized exploration. In that literature, often people will study what's called Bayesian bandits, in which the planner knows a prior over the distribution class. But in the stochastic bandit literature, I'm assuming that this is the prior is unknown, and I'm looking at a worst case sort of bound. In particular, I'm going to try and minimize regret. So my goal is this quantity called regret, which is the difference between the optimal reward, the reward that the optimal algorithm would get over that time horizon T, minus the reward that the algorithm accrues over the same time horizon T. And the sort of, canonical result in the literature is that for stochastic bandits, the optimal regret is something like root T. So this big O notation is hiding logarithmic dependencies, but the sense of the result is that we can approach the optimal reward at a rate that's like T to the -1/2. So this convergence is sublinear in time. And this also shows that we're approaching this very strong bound, which is the optimal reward at time T. And hence this bound is also an upper bound on the reward of any Bayesian planner but it doesn't use his or her prior. And so in other words, even in a Bayesian setting, the policies that satisfy these sorts of regret bounds are asymptotically optimal. Now, returning to the problem that I have at hand, when we have a recommendation platform like Yelp, it's clear, the arms here are the pizza restaurants, but it's clear that I can't just run an off-the-shelf multi-arm bandit algorithm, because I can't insist that a particular customer go to a particular restaurant when I want to explore that restaurant. And so prior work has dealt with this problem, as I mentioned earlier.
So Nicole, one quick thing before, just in terms of the modeling, so the base assumption of the standard bandit setting to this, to the restaurant problem would assume that the restaurant quality is something that is fixed and it sort of stays.
That's called collapsing arms. So I'm actually looking at stochastic. So every time I cook a pizza, the quality of my pizza is drawn from some distribution.
But if I look at the experience that I get as a consumer, that could depend on the, not just the pizza, but maybe also how many people were there, how long my wait was. I mean, that could vary. There could be a load dependent latency term or whatnot.
Sure, that's different than the first point you raised. So the first point you raised is that the arms might collapse, or you could have what's called collapsing arms, which is that, I don't know the distribution of the reward, but it's the same every day. So as soon as I pull the arm, I know the distribution of reward. Okay. And that is actually the first paper that started this literature in the economics, was studying this collapsing arm setting, which, as you can imagine, is in a sense much easier. The second point you raised is that there could be some context, and the context could even be endogenous to the policy of the principle. And so there has been some work in very recent looking at contextual bandits with incentivize, with strategic agents. But I'm going to not use that. You can assume I'm having takeout or something.
All right, thank you. Yeah.
So prior work asked how we could use, get the principle to induce exploration among the agents. And as I mentioned previously, the idea of the principle of the prior work is that only the principle knows the rewards of the past arm pulls. So this would be an assumption that, customers have their pizza and then they enter a review into Yelp, and Yelp is the only entity that has access to the full set of reviews. If other customers get access to these reviews, it's only because Yelp chooses to reveal them. And so in such settings, the prior work noted that the principle could recommend exploration to each agent with small probability. And if that probability is small enough, then, and otherwise the principle would recommend exploitation, which would be, the principle would calculate which restaurant is most likely to have the best pizza and tell the customer to go there. And so this exploration with small probability is going to be incentive compatible. That is, the agents will be incentivized to follow the recommendation of the principle if the probability of exploration is small enough, because each agent doesn't know whether she received an exploitation or an exploration recommendation. And so she will just, it's in her best interest to follow the principle's recommendation. Alternatively, prior work explored how we could maybe pay agents to explore. And Yelp does this to some degree. There's a Yelp cashback program. And so you could imagine paying people to go to certain restaurants over other restaurants. And if I pay them the difference in their utility between exploration and exploitation, then I can indeed overcome this, incentive constraint and get people to explore as often as I want if I have enough of a budget. So this is the prior work. There's the results that they managed to get is like optimal regret bounds, which is pretty awesome. So they can match the optimal regret rates that I showed you in the multi-arm bandit problem, even in the presence of these incentive constraints. And they do so using this model in which the principal can commit to a signaling scheme. That is, upfront, the principal can commit to a mapping from any history of rewards that she observes to a recommended arm. So for example, in this recommend exploration with small probability, the committed policy is, I'm going to flip a coin, and if it comes up heads, I'm going to tell you what restaurant is in your best interest. That's the exploitation. If it comes up tails, I'm going to tell you to explore, and I commit to that up front. Also, we then, this prior work had agents sequentially choose arms based on their prior, the signaling scheme, and the recommendation. But the first thing that these papers observe is that without loss of generality, we can assume that the scheme is Bayesian incentive compatible using a sort of revelation principle argument. And so agents are incentivized to follow the recommendation. And hence, we don't need to think about what information we provide to agents. We just need to tell them where to go. So it's like you log into Yelp and it just gives you one restaurant and says, go there, with no explanation. And so using these kinds of techniques, they get optimal regret rates. What we wanted to ask is, like, what happens if we try to alter the assumptions, these standard assumptions? And we wanted to look at something that might have a little bit more of a robustness flavor and relaxing the rationality of the agents. So I wanted to understand what would happen if the priors are incorrect. Like, can I come up with a prior free or prior independent model that still gets good regret? That's certainly possible in the multi-arm bandit literature. So what about in the incentivized exploration space? And then also, is it okay to assume that agents do these Bayesian updates correctly? Can we maybe relax that assumption and have a simpler behavioral model for the agents? On top of that, do the agents trust the principal to implement the policy that they've committed to? Randomization might be hard to verify, and also a lot of these policies have a lot of complicated sort of descriptions that could be hard to monitor. And then you could also ask, in sort of a transparency context, is it feasible in the context of a recommendation system like Yelp to just reproduce a single recommendation with no justification? Or do we need some degree of transparency? Do we need some sort of justification explanation as to why Arturo's is a good restaurant for you to go to in the context of past reviews, for example? And so we address these sort of philosophies, these considerations in our model and in our results. So we're going to assume that the agents are frequentists. This is relaxing the rationality constraints, or rather introducing a different behavioral assumption. And I'll define it more precisely in a few moments. We're also hand in hand with that, it's important if agents are just acting on data, that the data be in a sense unbiased. And so we're restricting the signals to be what we call subhistories. And this in a sense also relaxes the commitment assumption, because it's easy to verify if you have an external agency that is monitoring the principal. We also then look at the stochastic bandit setting, so we're not relying on priors. And in that setting, we develop a simple scheme that gets sublinear regret and a layered scheme that gets optimal regret. And the idea, sort of the easiest takeaway, is that it's useful to group agents into focus groups, and each focus group does their own exploration naturally, and then because of the randomness and the stochastic rewards, you'll get many different outcomes in the different focus groups, and that'll provide enough exploration naturally, enough natural experimentation for future agents to make the right choice.
So Nicole, the subhistories are sort of provided ahead of time in your context. So that's what you meant by commitment. It's all, the whole thing is laid out saying, at this time, if you appear, you see this history and so on.
Yeah, so there is a commitment in my model for sure. I'm not saying that we don't need commitment. I'm saying the thing that we commit to is arguably more monitorable, or like I'm missing the word right now, but like a regulator can go in and check that that policy is what was happening, because they can go to the people that provided the reviews and make sure that those reviews are true, and the principal can provide the partial order up front. So there's a bunch of related work. I'm mostly familiar with the related work in the economics literature, which is more or less my home community. And so this is a sort of repeated Bayesian persuasion game, if you think about it, because every day the principal has some information and is trying to incentivize the agents to take certain actions. So there's been a lot of work. It's a really hot topic these days, this Bayesian persuasion literature. And some of the papers that I've highlighted here are looking at things similar to us, in the sense that they're asking what could be achieved in restricted message classes for the principal. There's also a literature on hard information and voluntary disclosure. So these literatures assume that you can't, there's some facts out there and you can selectively decide what facts to reveal, but you can't manipulate the facts. And so our model has this flavor because the principal can reveal a subset of the reviews, but can't change a review. And then, our work is motivated by this idea of recommendation systems and the accompanying rating systems design. And so there's a bunch of work in the econ and OR literature looking at rating systems, things like endogenous entry of firms when there's rating and reputation that they have to think about. So this is a bunch of stuff that you can go read up on if you're interested in this kind of stuff. So let me get into my own results. I have a setting with 2 arms, and we can extend this to any constant number of arms, but for the purposes of the talk, it's convenient to think of 2 arms. There's a Bernoulli mean reward, mu A, which means that the reward of the arm A is RA with probability mu A. The reward RA is 1 with probability mu A and 0 otherwise. And I'm going to label arms such that arm 1 is the better arm for convenience, but of course, the principal and the agents do not know this. Each time T, an agent is going to arrive and choose an arm and then receive a reward, which is drawn with a Bernoulli according to the mean reward of the arm. And the signals that the principal can provide are what I'm calling subhistories. So that is for at time T, the principal looks at all past reviews, all past time steps, what arm was pulled and what reward was received, and provides the agent at time T with a subset of these reviews. So my behavioral model, I'm going to assume that the agents, when they see one of these subhistories, so what is a subhistory? It's just a list of past rewards of an arm. So the agent is going to calculate the empirical mean reward in that list for each arm and the number of pulls of each arm. And then they're going to form estimates of the Bernoulli parameter of the arm so they're going to form an estimate of the mean that is close to the empirical mean. And I'm not restricting their behavior beyond that. So they can, if, for example, some arm has very few pulls, then the agent can be super pessimistic about arm 1 and super optimistic about arm 2. That's fine. But as the number of arm pulls gets larger and larger, I want the estimates of the agents to converge to the empirical mean. And then the agent's going to form all of these estimates, all of these mu hats, and just select the arm that has the highest estimate. Now, hand in hand with that, I'm going to look at a signal policy that is transitive. So this says that when an agent is presented with the history of someone, they also see all the things that that agent saw. And so this relieves the agent of the need to reason about why people took certain actions. They have all the information that those people had available to them when they made their choice. And so if they wanted to, I mean, of course, my frequentist agents don't do this, but if they wanted to, they could reason about why certain choices were made. And so by relieving them of the need to do this kind of reasoning, I'm making the frequentist model feel more justified. I'm also, and this is, I think, even more important, going to insist that these signals are chosen ex ante. So this is what BJ was referring to, and what I meant by saying that the data is not biased. So that is, before anyone comes in the door, I'm going to decide which agents see which past reviews. So this might be a policy that says on even days, anyone who comes in on an even day is going to see all reviews from all even days. And anyone who comes in on an odd day is going to see all reviews from all odd days. Now, this is important because let's suppose that the principal was able to change. So the principal noted that the outcomes of the reviews were maybe as follows. So the diamond arm, the first day got a high score, and on the third day, it also got a high score. And also the triangle arm got low scores on these odd days. Whereas on the even days, by chance, the triangle arm was doing well and the diamond arm was doing poorly. And so if the principal could choose which history to give the incoming agent upon arrival, the principal could just think, okay, if I want him to pull the diamond arm, then I can give him the odd histories. If I want him to pull the triangle arm, I should give him the even histories. And so if this kind of manipulation is going on, then a frequentist response is not particularly reasonable, because the agent should know that the principal is trying to trick him. So I think the model here is one of our main contributions. I like this idea of disclosure policies. One way to motivate the transitivity and what's called partial order assumption on these policies, these two things I discussed on the last slide, is that from an agent's perspective, they're basically seeing the full history of some alternate reduced world in which only the people in their history existed. And if an agent is seeing the full history, then this sort of frequentist behavior seems like a reasonable assumption. Another point I want to make about this model is you can interpret the construction of these partial orders as some sort of principle constructing a social network and then letting the agents engage in social learning. But let me get to some of the technical contents. So the design goal here is to minimize regret. Now, since I've assumed arm 1 is the optimal arm, that's just t, the time horizon, times mu1, minus the expected reward that's received at each time t. That's the optimal utility and the utility induced by the policy. And I'm going to do this in worst case over the realization of the mean rewards. So there's two things that are pretty natural. The first attempt would be, what if we just show everybody everything? Then in that case, actually, the agents may end up hurting on a suboptimal arm. And this should be somewhat intuitive if you're familiar with the literature on information cascades. It actually takes a little bit of work to show this, but it's, I think, something you might expect. The other thing that would be natural is to give no history at first, and then after some amount of time, start showing everybody everything. And this is actually a pretty good policy if you know the gap parameter. So in multi-arm bandits, there's this gap parameter delta, which is the difference between the reward of the best arm and the second best arm. And if you know the gap parameter, then you know how many agents you need to distinguish which arm is the better arm. This is assuming that each agent, when they have no information, picks an arm at random. You can get around that with a small trick, which I'll show you next. But if you do have that assumption, then you can use this theorem from statistics that explains when we can distinguish biased coins in order to get low regret with respect to this gap parameter. What I'm going to show you now is how to leverage these two first attempts to get a what I call two-level policy with regret t to the 2/3, a three-level policy that improves upon that regret. That's sort of an intermediate step that I think has some interesting takeaways of its own. And then finally, an L-level policy with regret that approaches t to the 1/2, which is optimal. And one thing to note is that in the multi-arm bandit literature, the optimal regret with non-adaptive policies, that is policies that decide up front how much exploration they're going to do, is t to the 2/3. And the optimal regret with adaptive policies is t to the 1/2. So the whole trick from moving from 2 levels to L levels is to figure out how can we manage to get adaptive exploration despite the fact that we're insisting on designing the network structure up front. So let's start with our simple policy. So the idea is to combine these two first attempts, full history and no history at first. In level 1, I'm going to have a bunch of copies of full history. So this would be like every Monday agent sees all the Monday reviews, every Tuesday agent sees all the Tuesday reviews, and so on. And then I'm going to note that because this full history can herd on the suboptimal arm, each arm is going to get sampled with constant probability in level 1. And then, so now I don't need this random choice assumption that I discussed earlier. Now in level 2, I'm going to combine all these level 1 histories, and the agents in level 2 will see many samples of each arm because each arm was sampled with constant probability in each full history, and thereby be able to identify the better arm. And so we need to set up the parameters such that we get a good regret bound, even though we don't have access to the gap parameter of the instance. And in order to do so, we just need to make sure that there are enough level 1 paths such that if the gap parameter is large, then the level 2 agents are able to distinguish it. And if the gap parameter is small, then it doesn't matter if we all pick the suboptimal arm forever because it's anyway almost optimal. So again, the intuition is that the level 1 agents are going to provide enough exploration to distinguish the better arm if the gap is large. In order to improve this t to the 2/3 bound, we're going to need adaptive exploration. And so let's see how we can get adaptive exploration with these policies. I'm going to first introduce a suboptimal policy that has some intuition, and then I'll mention the optimal policy and not really prove anything about it. So the policy that improves on t to the 2/3 is a very natural idea. I have this 2-level policy I showed you. What if I create many copies of it and then button them all up with a bunch of level 3 agents? Now, the level 1 agents are going to be in charge of exploration, and the level 3 agents are going to be doing exploitation. And these level 2 agents, what's very beautiful about this is these level 2 agents are going to exploit if there's a clear winner. And if there's not a clear winner, then they're going to do more exploration. So why is that? Well, if there's a clear winner, then in other words, if the gap parameter, so if the gap parameter is negligible, as before, I don't care which arm people pick. If the gap parameter is large, then the analysis from the 2-level case goes through, and level 1 has a sufficient exploration for even level 2 agents to exploit. But what happens with a medium gap? Well, with a medium gap, arm 1 is identified in aggregate in level 1, but any level 2 agent doesn't see enough level 1 agents to know that the arm has been identified. And so the level 2 agents are at a disadvantage, but the level 3 agents can all pull arm 1. In the small gap case, on the other hand, so there's 4 cases about that I'm doing a case analysis of the gap parameter. So in the small gap case, the level 1 agents don't do enough exploration for level 3 agents to exploit. But because of that, we also know that level 2 agents aren't able to exploit. And so some level 2 agents are going to be, there's always some level 1 group such that, say, the triangle arm got lucky and the diamond arm got unlucky. And those level 2 agents that are aggregating that particular level 1 group are going to pull the lucky arm and not the unlucky arm. And conversely, there's always some other level 1 group where the other arm was lucky. And so the level 2 agents are going to, in the small gap case only, provide us with additional exploration. And that's how we got adaptive exploration in this incentivized exploration setting. Now, we would love to extend this, you can work out the parameters and see, what boundaries do you need between negligible, small, medium, and large for the gap parameter, and you'll realize that you get a regret bound of t to the 4/7. And so to improve on that, we need to do even more adaptive exploration. And so the L level policy is going to create multiple levels. Each level is intended to distinguish instances with a smaller and smaller gap parameter. So for any particular gap parameter delta, there's some level L that's supposed to distinguish it. And the first attempt you might want to do is to create an L level MRE tree. So we just create many copies of that 3-level policy and button them all up with level 4 agents and so on. This does in fact provide adaptive exploration, but it also has a really terrible regret bound because there's many, many agents in the level 1 group. There's exponentially many agents in the level 1 group. And since these people have very little information, I'm not able to bound the regret of these people and hence of the entire population. Instead, we're going to have to reuse samples. So this is like the third main idea in the paper, is that you need to reuse information in order to get the right regret bounds in this policy. And with the optimal sort of interlacing of groups, we can set parameters to get a regret bound that approaches t to the 1/2. The policy is a bit complicated, so if you want to look at it, you should look at the paper. I think the main takeaway from that is that it can be useful to reuse information in these kinds of settings. You need to be careful about exactly how you do so, such that you don't pollute the information, because we're really relying on some amount of independence of like experiment outcomes in order to incentivize exploration. So the main result, let me conclude with some takeaways. The main result in the paper was an optimal regret in our model of selective data disclosure with frequentist agents. The model was one of the contributions. It relaxed, or at least introduced, a different sort of commitment assumption. It changed the rationality, it relaxed the rationality assumption and replaced it with a behavioral assumption on the frequentist agents. And it robustly achieves asymptotically optimal regret in the sense that it does so in the worst case over priors. The main ideas for generating the results were that we have a 2-level policy that used focus groups of agents to induce exploration of arms, and that wasn't sufficient for non-adaptive exploration. We then introduced a 3-level policy, which had, as in addition to the 2-level policy, these group aggregators. So the intermediate level were these group aggregators that refined exploration before the final level, who was able to do the exploitation. And that enabled us to do adaptive exploration, even in the presence of incentive constraints with an ex-ante defined network. And then finally, the paper goes on to show how to get optimal regret by reusing exploration. Thank you.
Thanks, Nicole. So I had a few questions. I don't know if anyone else has or not, but let me ask my question. In the L-level interlacing part, I think I guess you're going to interlace across these 3-level groups and 4-level groups and so on. So for part of it is to control I mean, you had this tree with the exponential increase to sort of control that farm out in some ways. Right?
Yeah, so the interlacing is gonna, there's gonna be level 2 agents that see subhistories or level 1 groups. Like there's basically a bipartite graph between level 2 and level 1, and there's cycles in this graph. It's not a tree anymore, but it's in such a way that the arms, so I still need it to be the case that when arms get lucky in the level 1 group, there's just a constant number of level 1 groups that cause a bunch of level 2 agents, that the arm only needs to get lucky in that set of level 1 groups in order for the level 2 agents to do further exploration of it.
Okay.
So yeah, I have it in my longer version of this talk. I could try to pull up those slides, but
I can see how that'll be. You have to be very careful in the way you construct it, because you don't want.
Yeah.
It's interesting that it can be done. Any other questions from anyone? If you can put it on chat, I can basically mention to the speaker. I mean, I wanted to ask these questions before we go into the discussion part where there will be more formal questions coming through. Okay, if there isn't, then maybe we'll do the following. I will start the first part, and then my student Shitan will pick up the second part.
Great, so I should stop sharing, I guess, right?
Yeah, I should just stop sharing, and then I'll bring it up, and then we can go back. Yeah. Oh, yeah, now I need to share something. Which one? No. There it goes. Let me take it this way. So yeah, Nicole, thanks so much for a very nice talk. I think I read the paper too, but I think I got a lot out of it by your talk as well. So I'm going to give a more bandit type perspective to what you maybe point some connections to some bandit literature, and in some sense to what is the literature known as adaptive control, because some of this, a lot of these sort of questions, not the incentivized exploration, but the whole space has been explored well in that context. So let me start with a preview. What is this thing called self-tuning adaptive control view? So the same basic problem, your stochastic bandits, you have K Bernoulli arms with means. I'm just ordering M1 is bigger than 2, bigger than 2, 3, so on, so bigger than K. I'm going to assume I see a full history. So I forgot the time index, but if you're agent T, you get to see all the arms that were pulled by the previous agents and also the rewards. And so conceptually, I'm sort of working with the fact that you can get cascade type behavior. And the way to think about it is, okay, so conceptually, the adaptive control view takes the following viewpoint. This is my problem specification. I don't know the muse, but I know it's a Bernoulli arms. So what I'm going to do is the agent follows this conceptually, does this. He assumes the means are B1 to BK. Based on that, he evaluates the likelihood of this history, and then sort of finds the maximum likelihood estimate, which is capital B. So capital B will be my maximum likelihood estimate of it. And using this maximum likelihood estimate, he basically finds the best arm and plays it. Right. So, and this would be very simple. In this case, it will just be the number of arms you played and take empirical means. But conceptually, it could be a more complex problem. So this is why they take this viewpoint. Right? Now, if you in the viewpoint of adaptive control, this is what is called a certainty equivalent control. Basically, you have a policy of some kind. You look at how it plays out. You form a maximum likelihood estimate, and then you sort of adapt the policy as you go. So it's a parametric problem. You know the optimal policy for each parameter. You estimate the parameter using a maximum likelihood, and then use an optimal control corresponding to that, and just run this through. Now, interestingly, control has a dual role. It basically helps you estimate, sort of explore this, estimate the space by exploring parameters, but it's also trying to optimize. This thing need not work in all contexts. It can work in certain contexts, and that's a big piece of work by Mandel in 1974, who sort of initiated some of these things. You need this thing called identifiability. And what it loosely translates to is that I'm talking about a case where it's not identifiable. If this property is not true, then it is identifiable. So if you're using a current estimate and its optimal policy, if you cannot distinguish between the current estimate and the true estimate, then your system is not identifiable. And coming up with an example is quite tricky, and there's a fantastic paper by Borker and Marai in 1979 in the transactions automatic control, where they show this for a more general class of problems. The standard textbook, which is used for stochastic control in many places, Kumar and Marai, discusses this viewpoint in integrated control. So in any case, once you have this, there are sort of different ways you can take this problem. And so I was going to talk about two different things. This is where, in terms of like a comment or whatnot, one was to come up with maybe an alternate sort of your disclosure policy, which could, I think, would achieve the same regret, at least in terms of the constants, not the constants, but in terms of the parameters. So the first one is sort of a forced exploration scheme. And this falls from this literature. I'll tell you one key reference there. So you add two phases. So you think of it as two phases. One is the forced exploration phase and followed by an exploitation phase. Now the forced exploration phase is basically going to randomly try, agent in a forced exploration phase will randomly try all arms. You fix the duration of this forced exploration such that all arms are explored at least once. So this is a coupon collector type problem. You can, with high probability, you can achieve this point. The exploitation happens after the forced exploration, and I'll discuss this a little later. And more importantly, the duration is tunable, and this is going to be important to achieve low regret, right? Because in any such scheme, eventually you have to be exploiting much more than you're exploring, and that's how you gain. Right? So I'm going to consider this whole scheme in terms of epochs, and in each epoch there will be a forced exploration phase in the beginning, followed by an exploitation phase. Now I'm going to construct the same sort of the partial order by allowing so the forced exploration phases, they are just going to do forced exploration. I'll tell you how to achieve that in some sense. The exploitation phase will see the history of all past forced exploration phases. That's the only history they're going to take. And the agents will basically form a maximum likelihood estimate based on that. This is a frequentist, and choose the best arm and exploit. So that's going to be the way that epochs are. And what I'm going to do is basically increase the exploitation phase duration slowly in each epoch. And this is the and I think it has to be a certain, I don't exactly remember the rates, but loosely speaking, that's what will happen. You cannot, so this scheme will asymptotically learn the best arm. And I think there are results, I don't know the paper exactly, which shows good good regret performance as well. So one of the papers that will actually discuss the scheme for the bandit context, and actually in a more general context, is this Agrawal and Teneketsis from 1989 in Systems and Controls letters. So as I said, this scheme can also fit in the results that were presented earlier. So the forced exploration can be created by revealing no history to the agent. Then the scheme, and once you do that and you have this natural order where the exploitation phase gets to see all the past history, then you have this partial order. The only thing in some sense is the scheme isn't, behaviorally it may have a problem, because if you look at it, my time index can be very far out. I'm like the customer 1000, but there is a chance I get to, I mean, this is all revealed ahead of time. I'm the 1000 customer, but I may be seeing no history. And that is something that I may not accept if I am a person in the system. Putting that aside, this scheme will give you a sort of a graph structure which is simpler, which will sort of get you the same regret in a way. But of course, it misses that caveat, and I will accept that. So that's one sort of side of it. The other side is I'm switching. It's not so much with the paper you presented, but more with the general sort of payment-based schemes. There could be an alternate way to think of these payment-based schemes, again, in the context of this adaptive control literature. And that follows from what's called the biased maximum likelihood estimate policy. So just to so you can, so I'm going to again revisit the self-tuning adaptive control literature here. So if identifiability holds, then certainty equivalent control using maximum likelihood will asymptotically converge to the optimal parameter. And that's a scheme that you can use. But if identifiability doesn't hold, then there is a bias likelihood, maximum likelihood scheme, which actually is general. It applies in both cases, which will asymptotically identify, will give you convergence to the optimal parameter. So let me first describe the scheme. So I'm going to think of my parameter as B, which lives in some space, and think of in the bandit context, this would be the means. So at the nth agent, I have if I think the parameter is B, I have a certain likelihood function, ln of B. In this problem, I'm going to assume that if the parameters are B, I also have a value function of the optimal policy for that parameter. So I call that J of B. So now if I can make if I can change the maximization that agent N is doing to not be the likelihood function, but this particular bias likelihood function, where basically I take ln of B, multiply it by Jn to the B raised to the power minus Fn, where Fn is a sequence that increases to infinity fast enough. It can't be too slow. It cannot be too, I think. Then what is known is that basically these things will converge asymptotically to the optimal parameter, and you'll get the optimal policy. And I think the best choice of this function, it cannot go slower than it is for some C log n in some sense. And this is actually some papers again from 1980s. This is Kumar and Becker and Kumar and Lin. So it's called the Kumar-Becker-Lin scheme. The caveat here is you need to know the value function, which could be very hard, complex for a very hard problem, for a general problem. So in the particular multi-arm bandit problem that you consider Bernoulli arms, this J of B is actually very easy to compute in closed form. And this bias maximum likelihood actually has a nice form here where it's like you add something to the number of times you've explored an arm based on the parameter that you assume. And in fact, Kumar, who's the same author from 1982, there's a recent work in ICML 2020 which establishes good regret for such policies, for this policy, this class of policy. Now, the way this will help in the payment scheme is basically if I take logarithms when we get a payment scheme, because it's sort of naturally you get the quasi-linear form. So the function is going to be, there should be a log, which I somehow got dropped here. It should be so the price function for agent N is Fn times log of JB, if the report is B. And so this will then incentivize agents to take the bias maximum likelihood action and learn the good regret. So anyway, this is all I had. So I'll let you know to add any comments or anything that, let me end my show. Yeah.
Yeah, thank you. I think that was very clear and interesting. I think that the policy of forced exploration is an interesting one with that one drawback that you mentioned. I mean, it's, I guess on the flip side, it has the benefit over the other one that I didn't fully present, the L-level policy of being perhaps easier to explain in a talk. And I guess therefore also maybe arguably simpler for agents to comprehend.
So there was a question here, I think from Shitang. So he says, correct me if I'm wrong, the forced exploration scheme could make every agent all explore a subset of arms if agents are uniform and unlucky bias. So I'm assuming here it's the stochastic bandit, so you don't know, you basically uniformly explore arms. So I just want to construct the duration long enough that with high probability all arms are explored.
Yeah.
So Shitang, I've stopped sharing. If you want to share your slides, you can.
Okay. Okay, so I will discuss from another perspective, the information design perspective about this paper. So I'll quickly just recap the models. So we have a sequence of myopic agents, and we have finite actions, finite arms to choose. In this presentation, that there's only 2 arms, but in the paper, there are multiple arms are allowed in the model. Each agent just receives a message from the principal before choosing arms. So this is quite different from most of social learning literatures, because the whole information structure is kind of all being chosen by the planner a priori. It's there's no private signal that's solely owned by each agent. But this will be one strength in this work I will discuss later. So the rewards of arms are binary, but drawn from a Bernoulli with a Bernoulli distribution with unknown mean. And the planner's problem is trying to minimize the regret. So this will be the multi-unbound problem in the social learning. So the main message in this paper, I kind of think there are 2 main messages. One is that the message can actually alter the agent's incentive toward exploration by constructing information structures. And the message actually contains unexploded and all the realized rewards. This is one assumption for the message. And there's a very important assumption for the message, the unbiased subhistory, or kind of transitivity of the message is that we don't need to guess the reason behind the predecessor actions. So with these assumptions that we don't need to worry about your predecessors are non-Bayes rational, or they don't have the same exploration estimation functions the same as you. So once you have transitive subhistories, then you don't need to worry about that. Then the second message is that I send more information. The most information, the full history disclosure in each turn can induce herding. So this definitely will be a kind of the worst, not the suboptimal policies that we are going to use. So I want to briefly talk about what I like in this paper. So I like one assumption that no transfer is required to incentivize exploration in this paper, because so we don't need to worry about the principal agent problems from the platform to the agents, and there's also no payment or no transfer among the agents. So the agents are kind of voluntarily disclose their information. The second one I like is that there's no assumption on prior belief or of rewards. So it can support any prior belief or rewards, even though it's really biased and very far away from the true mean. With the exploration in the mechanism can actually overcome that. So we don't need to worry about if we need a common prior for every agent, or we have diverse agents. I think this is very great assumption relaxation in this paper. The third one is that I think that there's a very weak assumptions on reward estimation functions. So we only need the estimation function. The estimates are close to empirical average after long enough explorations. So the decision does not need to rely on the Bayesian rational of choice of their predecessors, and it also allows a time invariant estimators. It's like that every agent has slight different estimation functions, but they can still work together, and they still can be covered in this paper. So from the information design perspective, I have 2 following questions. The first question is that it's motivated by the Asimaglu's paper in 2011, the social learning one. So currently the history of disclosure, the path, the topology is kind of being predetermined and fixed. But Asimaglu's paper kind of tells us that if we have a randomized history disclosure, it might help to reduce the number of agents required to achieve learning, syntactic learning. So is it possible that we are kind of introduce a randomized history disclosure but we still need to satisfy the transitive assumptions. So it's kind of randomized in the principle, but once an agent, once the agent, before the agent get to see the history, it's kind of the coin is being tossed. Can this kind of randomized history disclosure can reduce the number of agents that required in the bottom layer? So we don't need that interlacing part, or we can afford a non-binary case because the current guaranteed bound is kind of exponentially. The number of agents in the bottom layer is kind of exponentially grow when you add additional arms. So is this possible to kind of exploit the Asimagu's randomized network topology idea in this work? That's my first question. The second question is that I was thinking of that, is it possible to consider kind of an online or interim policy of the history disclosure? So this is kind of trying to incentivize the agents, but not ex ante. It's kind of trying to force the agent to explore, but conditional on what else is currently being explored. So if agents are uniform, then kind of an interim policy does not really help. But if agents are diverse enough, can we assume that if NT can be determined condition on what arms are explored in the history? So, but in order to avoid malicious platform and incentive compatibility issues, maybe we still need the policy cannot depend on the realized rewards, but it can only depend on what arms being explored. But is this a way that we can try to step on the current result to get the results in a multi-arm, not just 2-arm or 3-arm, to make the bottom layer will not grow exponentially? That's my question.
Thank you. That was very interesting. I think if the Asamoglu paper you're referring to is the one with like Ilan Lobel and students, I thought that paper was in a sort of social learning model where agents observe actions but not rewards.
Yes.
I think so I'm not entirely sure about the answer to your question, but I think that is actually a pretty significant distinction between the two models. And
yeah, I noticed this because we now have rewards, and we need to kind of estimate the meaning of the rewards, right?
Yes, we need to estimate the meaning of the rewards, but there's no like private information in a sense, and that like it's not that the agent had a private signal that they chose an action based on that I as a future agent don't observe. So I think it's a good question that you ask. I don't see a way to use a randomized.
What I think maybe let me add one thing. So I think that no private signal is kind of not that important, because that the current reward, like the reward that the current current agent get is kind of the private signal for the first one observe the history of this agent. So you can view that one's private history is his immediate predecessor's reward. If you do it in that way, then these two models are not that distinct.
That's true when you break the transitivity assumption. But if I have that transitivity assumption, then I see everything that agent saw. So
you see everything that agent saw, but you also see that agent's reward. But when that
agent's reward as being the private signal that the next agent gets in that sequence.
Yes,
I guess
yes,
that's
which actually did get what I say.
Yeah, but in the in the standard social learning model, there's some private signal that I never see, like from past agents. Like kind of the current agent having a private signal not who's private to whom, like it doesn't matter really to anything in the future that the past didn't see that signal. So I mean, maybe we can discuss it more offline, but I think that there's some substantive difference here. But that doesn't mean that there's not a way to use a randomized disclosure. Like every time you could have the agent hook into a random part of the current graph and observe the subhistories from that point. And you could ask if that helps reduce the number of agents in the bottom layer. I don't see a way to make that happen right now because you kind of lose control over the size of the bottom layer with a bit, and but yeah, it's something worth thinking about. Another thing to notice is that we are getting optimal regrets. So this would be asking to improve on this objective that every agent sees a substantial fraction of the history present at the time that they enter the system. And I think that's a very interesting direction for future research that like actually should matter to systems like Yelp. For the second question, you're asking if we can choose conditional on what arms are explored, like choose the subhistory. So now we're not going to be choosing it ex ante, but choosing it when an agent comes based on which arms are explored, but not on the set of rewards that were received in that subhistory. Now, I guess I could try to leverage this to perhaps improve exploration. Like, you know, I can just show you a subhistory in which only triangle arm was explored, or only the diamond arm was explored. Of course, this is going to risk situations in which agents that are only seeing triangle arms will herd on the wrong triangle arm outcome. But maybe if you have enough of those in parallel, it could work. I'm not and then maybe you could reduce the number of agents in level 1 by a constant factor, but I'm not particularly hopeful that you could do much more than that. But that's also, yeah, an interesting thing to think about.
Actually, I had a question which is sort of parallel to what Shitan asked. So there is in the Bayesian social learning context, which is the paper where Asimoglu and others, Amlo is that there, I mean, so it's a randomized sort of history that you display. I think there's an open question there whether you can do it with like a deterministic, similar to your problem. So in a way, is there a way to take the other side of the question, that you have a deterministic network in which you're revealing information and still sort of get asymptotic learning in the context of the Bayesian social learning problem? And I don't know. I mean, this is
possibly, I think you probably need at least some parallel of the frequentist assumption in that space. I haven't read that paper in quite some time, but I recall they were doing like Bayesian updating and everything, right?
Yeah, they're doing Bayesian updating. That's right. Yeah, yeah.
So possibly with some, like our model might shed some light on that if you have the appropriate behavioral assumption. If you just want to do their thing with a deterministic, like their exact model, but set up a deterministic network and try to get asymptotic learning. I don't understand why that's hard per se. Like, can't you just, if that's all you want, you can just wait sufficiently long without displaying, you know, without giving anyone any history. And then with high probability, the information has been aggregated, and then you can give people. But then
you don't necessarily get asymptotic learning, right? So there is still a probability of going wrong in some ways. You want the probability of taking the wrong action to go to 0 as.
Well, it depends on the order of quantifiers. Like if I can pick the length of people that don't learn as a function of the time horizon.
Yeah, so in that problem, you're looking at time horizon going to infinity in some sense. You're
yeah, but can I you know, is it that I can pick a different policy for every time horizon, or do I need to fix the policy up front and then let the time horizon
the
break?
thing is, can you you have to fix the policy up front and for all time in some ways.
Yeah.
I mean, I think part of the issue there is sometimes you have.
And you could just do it exponentially growing, right? You can do that standard trick that, like,
yeah, maybe you
like
can talk
something interleaved, kind of like the policy you were recommending.
Yeah, yeah, maybe that would work as well. Yeah.
Which was deterministic.
Yes. Yeah, the post exploration. Yeah,
So I don't know, that it seems to me like that might solve the semantic problem, but I'd have to think about it more deeply.
all right, thanks so much. Are there any
Yeah,
other
thank you.
questions from anyone? Well, if there aren't, let me thank Nicole once again. I'll give you a clap per se. And thanks again for, so Nicole's meeting with a few people tomorrow as well. So thanks again for coming to the seminar. Yeah.
Yeah, thanks for having me.
Bye.
Okay, bye.